Welcome dear learners. We are continuing Unit 3 Introduction to Nanomaterials. In the present module, we are discussing synthesis of nanomaterials, the bottom-up approach. In this module, we are discussing two approaches for the synthesis of nanomaterials as a revision. Introduction to bottom-up approach, popular bottom-up methods and selected bottom-up methods with their description. First of all, two approaches for the synthesis of nanomaterials. In the last module, we have discussed two important synthetic approaches we adopted for the synthesis of nanomaterials. The two synthetic approaches are top-down and bottom-up. As the name indicates, in the top-down approach, we are beginning from a bulk material. The important thing is that in top-down, we begin from bulk materials scaled down to nano. In bottom-up approach, we begin from small particles and scale up to nano. So, these are two important synthetic approaches for the generation or fabrication of nanomaterials. In the previous module, we have discussed several procedures that is popularly used in the top-down approach. And this module is especially intended to discuss the bottom-up approach, its different methods and their description with the examples. So, we are now entering into the detailed study on bottom-up approach. As I mentioned just earlier, nanomaterials here are synthesized by assembling small particles like atoms or molecules together. So, you have to keep in mind the fact that atoms or molecules are very small when compared with the nanoparticles. So, we have to assemble the starting materials, atoms or molecules to get somewhat bigger sized nanoparticles. The starting material in bottom-up approach must be in gaseous or liquid state. That is, we cannot do the bottom-up approach by starting from solid materials. We previously learned the fact that in the case of the top-down synthesis, the starting material must be in the solid state. Here in opposite approach, that is bottom-up approach, the starting material must be in gaseous state or in liquid state. That is, solid state sample cannot be used for bottom-up approach. We have to consider several bottom-up methods. There are so many top-down methods. Similarly, in bottom-up methods, there are also several different kind of methods. And in this part of the discussion, we are focusing on popular bottom-up methods. The popular bottom-up methods include chemical reduction. As the name indicates, we are starting from a salt precursor, a metal salt precursor or anything like that, and we have to perform reduction by using suitable reducing agent and convert that stuff into nanoparticles. That is involved in chemical reduction. We can study more details later in coming slides. Now, the second most important procedure, this is one of the most popular method also. This method is called chemical vapor deposition, abbreviated as CVD. In a similar sense, we can also say another method, that is physical vapor deposition, that we are not considering here. We are considering some important techniques only. First one chemical reduction, second one chemical vapor deposition or CVD, and the third method, this is one of the most popular bottom-up method, especially for the synthesis of silicon dioxide or silica nanoparticles. It is very important. This procedure is called sol-gel synthesis. We can study the details in coming slides. And the next method is hydrothermal synthesis. The term hydro represents water. You can use water or some other solvents, then the name solvothermal, thermal for heating. So, heating in water medium is the meaning of hydrothermal synthesis, and solvothermal synthesis means you are performing heating in some other solvents like alcohol, ether, etc. Now, another bottom-up method is the co-precipitation method. The term co represents together. Co-precipitation means we are performing the precipitation of two kind of materials together, or a same substance in different oxidation state. You are getting two compounds. For example, ferrous oxide and ferric oxide can be precipitated together. Such a method is called co-precipitation method. That co-precipitation method is also an important bottom-up method. Now, other bottom-up method is spray pyrolysis. Pyro is something related to heating. Lysis means fission. So, here you are adopting high temperature decomposition. That procedure is taken in spray pyrolysis. We can enter into the details later. And another popular bottom-up method is electrodeposition. One more method is also I have to mention. That method is called MBE, molecular beam epitaxy. It can be abbreviated as MBE, molecular beam epitaxy. So, these are various important bottom-up methods, and now we can take several popular bottom-up methods and study its details separately. First of all, among selected bottom-up methods, we are taking chemical reduction as the first part of our discussion for detailed study. In the chemical reduction method, these are very popular method or common method for the synthesis of nanomaterials. And in this method, in chemical reduction method, colloidal silver, gold, copper, etc. Colloidal silver, that means nano silver, nano gold, nano copper, etc. can be prepared by the reduction of their precursor salt solution. What do you mean by the term precursor salt solution? See, for example, in copper sulfate, copper 2 plus, copper is present in copper 2 plus oxidation state. So, in the case of copper sulfate is nothing but CuSO4. Here copper is present as copper 2 plus. If I convert to copper 2 plus to copper 0 state, then I perform reduction. For that purpose, I have to use some reducing agent. In a similar way, if I am taking silver nitrate as the precursor salt as AgNO3, silver is present in pleasant oxidation state. If I am using a suitable reducing agent like sodium borohydride or any suitable reducing agent, Ag plus is reduced to Ag0. Ag0 means silver in free state, silver 0 state in the atomic state. That agglomerated together to produce nanoparticles. So, here we have to begin from a suitable precursor salt solution of the metals whose nanoparticles to be prepared, then add some reducing agent. Subjected to reduction, metal in the positive oxidation state is reduced to metal in the zero oxidation state. That is the procedure occurring here. We can illustrate with some examples also. Now, in the chemical reduction, reducing agents like NaBH4 can be used under ice cold conditions because the temperature may influence the product formation. High temperature, low temperature, etc. are there, but low temperature or ice cold condition is preferred for reduction using selective reduction using sodium borohydride. Now, we are taking some examples. I already mentioned the fact that silver, copper and gold nanoparticles can be prepared by the chemical reduction method, and this is an illustration of the preparation of silver nanoparticles by using the chemical reduction procedure. Silver nanoparticles can be obtained by the reduction of their precursor solution, that is AgNO3. The most commonly used precursor for silver nanoparticle preparation is silver nitrate. We are taking a solution of silver nitrate and it is mixed with NaBH4. NaBH4 is sodium borohydride. Sodium borohydride is the selective reducing agent for this purpose, and the reduction is performed in ice cold conditions, and the reaction proceeds like this. Here you can see in the left hand side AgNO3. NaBH4 is the reducing agent. The reduction is performed in water medium. So, as a result of the reaction, let us look on our character, that is silver plus. Silver plus, what happened to silver plus? Here in AgNO3, silver is present as silver plus and NO3 radical has a charge of -1, and as a result of the reduction reaction, Ag plus is converted to elemental Ag or atomic level Ag, and here it is in zero oxidation state. That silver atoms connected together to produce silver nanoparticles. At the same time, NaBH4 get converted to BOH thrice, that is boronic acid, and hydrogen gas is liberated, sodium hydroxide. This is the balanced chemical equation for the reduction reaction. Without using this balanced chemical equation, this reduction reaction can be simply represented like this: AgNO3, this is nothing but silver nitrate, on reaction with the NaBH4. NaBH4 is a sodium borohydride. It is present in water medium. This is converted to Ag. These are silver nanoparticles. This is the simplest representation of this reduction reaction, but this represents this one represents the complete balanced chemical equation. You can remember this equation also. This is very easy to remember. So the reducing agent convert metal in the positive oxidation state to atoms in the zero oxidation state, which agglomerate towards together to get the nanoparticles. This is about the chemical reduction. Now, one more chemical reduction reaction. This we already just heard whenever we discussed the case of the Faraday's divided metal. I already mentioned that at that time the fact that Faraday's divided metal is prepared from a salt of copper, that is NaAuCl4, sodium tetrachloroaurate. There the reduction is performed by using phosphorus and carbon disulfide as the reducing agent. But here, in a common method for the preparation of the gold nanoparticles, we are using this technique. HAuCl4, this is simply the chloroauric acid, that is an acid containing silver. So it is nothing but gold. This HAuCl4 is an acid containing gold. HAuCl4 is converted to Au nanoparticles, that is gold nanoparticles are obtained from HAuCl4 or chloroauric acid by using a reducing agent, that is nothing but ascorbic acid. You are familiar with ascorbic acid. What is ascorbic acid? How you know about the name ascorbic acid? You are familiar with the vitamin C. Vitamin C is ascorbic acid. So in this transformation, HAuCl4 is converted to gold nanoparticles by usage of ascorbic acid as the reducing agent. In addition to ascorbic acid, here also we are using another reagent, that is citrate, or simply sodium citrate is also added during the reaction. Now we have to listen carefully on important thing. What is the need for adding sodium citrate in this reaction during the course of the reaction? What is the role? How it signifies? Why is it necessary? So many questions arises. Strictly speaking, it is very, very important to note that the gold nanoparticles are stabilized by citrate capping. What do you mean by stabilization? What do you mean by capping? What is the need for capping? You know, nanoparticles are highly reactive. When nanoparticles are prepared by certain methods, there is a chance for agglomeration or precipitation. That is, the nanoparticles may connect together to get the bulk material back in certain situations. In order to prevent the precipitation or agglomeration of nanoparticles to get the precipitate or the bulk material, we are using some reagents. These reagents are called capping agents or stabilizing agents. These capping agents cover each and every nanoparticle such that the agglomeration or precipitation is prevented. Here, if you are performing this reduction with ascorbic acid only, definitely you will get gold nanoparticles, but they may undergo precipitation to produce certain precipitate or the bulk metal back. In order to prevent that, in order to stabilize the gold nanoparticles obtained during this reduction reaction, we are also putting some sodium citrate. Sodium citrate contains citrate ions. That citrate ions cover or cap the obtained gold nanoparticles, and hence each gold nanoparticle will get stabilized. So, citrate acts as a capping agent, and major role is by ascorbic acid or vitamin C, which act as a reducing agent. So, in this complete transformation of HAuCl4 to gold nanoparticles or citrate capped nanoparticles, gold nanoparticles, ascorbic acid or vitamin C act as the reducing agent, and sodium citrate produces citrate ion which act as the capping agent or stabilizing agent. Hence, the result is citrate capped gold nanoparticles. So, in chemical reduction procedure, we are performing the reduction reaction of a salt precursor. You can perform reduction either in the presence or absence of a capping agent. Now we are moving on to second method, second bottom-up method. This is a popular bottom-up method, and this method is known as chemical vapor deposition. That is, we are depositing chemical vapors, vapors of some chemical compound, vapors of some salt precursors. Not every salt will undergo vaporization. So, we have to take some salt precursors which must be volatile. So, we are taking some volatile salt precursors and subjected to deposition of that vapors. This procedure is chemical vapor deposition. We can enter into more details of chemical vapor deposition, and in chemical vapor deposition, this is most popular method. CVD is a method to produce high purity performance solid, high purity, high performance solid phase materials. So, CVD is exclusively used for the preparation of nanomaterials in solid state, and this CVD involves the formation of nanomaterials from the gas phase, from the vapor phase, hence the name chemical vapor deposition. Gas phase at elevated temperatures, usually on to substrate or a catalyst. This implies we have to generate vapors of some volatile precursor salt substance. These vapors are subjected to deposition on a suitable substrate or a catalyst. Now, in CVD, a thin film is formed on substrate surface or a catalyst surface via chemical reaction of vapor phase precursors. That is, if you are using titanium tetrachloride, this is a volatile precursor. It is undergoing some vapor phase reaction, that is chemical reaction at the vapor phase, and that chemical reaction at the vapor phase generate titanium nanoparticle that may deposit in the form of a layer on the surface of a substrate or a catalyst. A precursor for CVD, chemical vapor deposition, has adequate volatility. Why we necessitate volatility as an important condition? Without the volatility, if the substance is non-volatile, then the vapors will not be produced easily. So, if you are taking a precursor, if it is highly volatile or if it is adequately volatile, we will get easily the vapors of that substance, and that vapors can undergo reaction at the gaseous or vapor phase itself, and then it can be deposited on the surface of a suitable substrate or a catalyst. And one more condition, this volatile substance must be stable also during evaporation. When in certain cases, during the vaporization of some substance, they may undergo some chemical changes also. So, whenever you are selecting a precursor for CVD, it must be adequately volatile, it must be stable also. These two conditions to be ensured prior to the selection of the precursor salt material for CVD process. Now, here there is a list of CVD precursors which are commonly used. Some halides can be used. What are the popular halides? This example will give you an idea. Titanium tetrachloride, it is a volatile precursor of titanium. This titanium tetrachloride can be used for the chemical vapor deposition preparation for titanium. Tantalum pentachloride, tungsten hexachloride, these are nice examples for adequately volatile halides which are stable also. And these halides can be used for the chemical vapor deposition preparation of titanium, tantalum, tungsten, etc. Now, instead of halides, you can use hydrides also. Silane, SiH for silane, GH for germane, NH3 is ammonia. These type of materials can also be used for chemical vapor deposition purpose because they are volatile also. Now, metal carbonyls, nickel tetracarbonyl is an easily volatile, adequately volatile carbonyl, and by using that, by using NiCO 4 times that, you can prepare nickel nanoparticles. There are several metal organic compounds. What are metal organic compounds? Metal with organic chelators, metal with organic ligands. Such a compounds are called metal organic compounds or metal organic frameworks, etc. Metal organic compounds also have sufficient volatility. They are stable also. They can also be used for the preparation of nanoparticles by using CVD method. During chemical vapor deposition, the substrate is exposed to one or more volatile precursors which react and decompose on the surface of the substrate or a catalyst. You can use a substrate or a catalyst on the surface of which the nanoparticles are deposited by the chemical reaction that occurring at the vapor phase of the precursor. Now, laser beam or plasma can be used to enhance the rate of reaction in chemical vapor deposition. This is one important thing. You can use laser beam to enhance, to increase the rate of the production of nanoparticles by using the chemical vapor deposition procedure. Volatile byproducts obtained during the process are removed by gas flow through a chamber. You know, this chemical vapor deposition is carried out in a closed container. During the formation of the nanoparticles, some byproducts or impurities which are also volatile can also be obtained during the course of the reaction. Such byproducts can be removed from the reaction medium or reaction site by passing some gases through the container. That is for the separation of impurities, for the removal of the impurities. Now, here there is a scientific diagram of the chemical vapor deposition procedure. Not a detailed study is required as far as your syllabus is concerned. Even though that is the case, I am here showing an outline, a diagram of a scientific diagram of the CVD procedure. Here there is a pressure gauge to control or to regulate the pressure inside the chamber. This is the CVD chamber. Here there is a furnace for heating. Here there is a substrate or a catalyst on the surface of which vapors can be deposited. Gas inlet, the material placed inside the chamber, titanium tetrachloride or nickel tetracarbonyl, they will get evaporated and some decomposition reaction occurs at the vapor phase. They will get a deposit on the substance of the substrate, or this substrate may be a catalyst. They generally deposited as a thin film. So, thin films can be easily prepared by the CVD procedure. Now, the next bottom-up approach, more or less this bottom-up approach got its popularity because this is a method for the preparation of more common nanosystem, that is nothing but silica nanoparticles. SiO2 nanoparticles or silica nanoparticles can be prepared by the sol gel method. For the preparation of silica nanoparticle, the sol gel method adopted is also known as the Stauber method. We can study more details of the Stauber method whenever we are discussing silicon dioxide nanoparticles, that is in your syllabus. So, we can enter into the general details of the sol gel synthesis. The sol gel method is a wet chemical technique. What do you mean by the term wet chemical technique? So, we are using aqueous medium, you are using water as a solvent. So, you are using solvents. So, a chemical synthesis performed in solvent is said to be the wet chemical technique. So, water need not be the solvent, you can use any other solvent also. If you are using a reaction in a solvent phase, then you can call it as a wet chemical synthesis or a technique. So, in sol gel method, there must be a solvent because it is a wet chemical technique. This sol gel method is the production of solid materials like metallic oxides, non-metallic oxides like silica from solution state reactants. That is, reactants are present in the solution state and the nanoparticles are obtained in the solid state. So, metal oxide nanoparticle, non-metal oxide nanoparticle like silica can be prepared by this sol gel synthesis. This method used for the development of various kinds of high quality metal oxide nanoparticles. Even non-metals can also be prepared. Typical non-metal is silica. So, why the name sol gel synthesis? What is a sol? A sol is a colloidal or a molecular suspension of solid particles or ions. Solid particles or ions in a solvent. That is, sol means simply a colloid. And the second one is gel. A gel is a semi-rigid mass that forms when solvent from the sol begins to evaporate and particles left behind it to join together in a network. So, first you have a sol or a colloidal solution, then the solvent will undergo gradual evaporation, then the particles are converted to the gel form, and gel form generate the nanoparticles ultimately. So, here there is a sol, here there is a gel. So, since these two parts are there, the entire synthesis is termed as sol-gel synthesis. In the sol-gel synthesis, there are several steps. There are several consecutive steps. We can move on to the important steps in the sol-gel synthesis. Or simply we can say that the sol-gel synthesis sift through the following 6 stages. The first stage is formation of stable solution of the precursor. Here we are taking a suitable precursor or a suitable salt, dissolve it in a solvent. That is the formation of a stable solution of the precursor. It must be soluble in a suitable solvent. So, the first part is formation of stable solution of the precursor. The second stage is the hydrolysis stage. The precursor substance undergo hydrolysis. After the hydrolysis, there may be more than one OH groups in the same molecule. That OH groups mutually condense together. That step is called condensation. So, followed by hydrolysis, there is condensation. That solution converted to gel, that stage is called gelation. The gel is undergo stabilization, that is called aging. And finally, water starts to evaporate from the gel, and that is called drying, and followed by densification. So, these are the 6 stages: formation of stable solution, hydrolysis, condensation, gelation, aging, and drying of the gel, drying and densification of the gel. These are various stages in which nanoparticles are obtained by the sol-gel process. So, there are 6 distinct stages. After this 6th stage, you will get a nanoparticle of metal or non-metal like silica. Now, there are several advantages of sol-gel synthesis. Since it is a very important process, we are outlooking what are its advantages. The important advantages of the sol-gel synthesis are here. You can control the particle size. Generally, sol-gel synthesis yield particle with a small size. Another part, better control over morphology of the particle. What do you mean by morphology? The appearance, its shape. In certain cases, the nanoparticle may be like a rod, so you can call it as nano rod. In certain cases, irregular morphology, the shape cannot be very well defined. In certain cases, the nanoparticles may be spherical. So, in the case of nanoparticle preparation using sol-gel synthesis, the particle obtained must have, same morphology, not different morphology mixed together, same type of morphology. For example, if you are dealing the sol-gel synthesis of the silicon nanoparticle preparation, we will get a spherical shaped silicon nanoparticles. Another one, this sol-gel synthesis is highly suitable for thin film deposition. We learned the fact that thin films are 2-dimensional nanomaterials. Thin film has to be deposited on the surface of a catalyst or a substrate, and you can easily deposit thin films on the surface of a substrate by adopting the sol-gel synthesis. Moreover, the sol-gel synthesis can produce high purity nanomaterials. That is, the nanomaterials obtained need not be purified, they are more or less highly stable. This sol-gel method can be used to produce powders and fibers. You know about the nanofibers. They are fibers in nano size, fibers with the nano size, nanofibers, nanometal oxide powders, etc. can be prepared by the sol-gel synthesis. So, these are very important advantages of the sol-gel synthesis, which is a very popular bottom-up approach. Now, we are discussing another important bottom-up method. It is nothing but the hydrothermal synthesis. hydrothermal synthesis. Hydro means something related to water. Thermal means temperature. So hydrothermal synthesis means you are taking a substance, dissolved it in water, that is an aqueous solution, and that solution is subjected to heating. So you are providing heat energy to an aqueous solution. Instead of water, you can use some other solvents. In that sense, in that time, we can call it a solvothermal synthesis. We can enter into more detailed study of hydrothermal synthesis. The hydrothermal synthesis is most well-known and extensively used method to produce nanostructured materials. Several kind of nanostructured materials can be prepared by this method. Metal nanoparticle, metal oxide nanoparticle, stable nanoparticles of different type can be prepared by the usage of the hydrothermal synthesis. Now, what we are doing in hydrothermal synthesis? In hydrothermal synthesis, nanomaterials are obtained through a heterogeneous reaction carried out in an aqueous medium. Remember, instead of water medium, you can use other solvents also. In that time, we call it a solvothermal synthesis. Here we are focusing on hydrothermal synthesis because our solvent is water. So, I took the salt, I took the substance and dissolved it in water and subjected to a heterogeneous reaction. And remember, this reaction is performed at high pressure and at high temperature. That is, for the preparation of the nanoparticles by hydrothermal synthesis, we have to heat the solution at high pressure as well as high temperature. So, this kind of reaction is not possible with our common test tube, and some special kind of instrumentation is required for the controlled heating at high pressure and temperature. How we can perform? Which vessel will support us to perform this hydrothermal synthesis? And for the hydrothermal synthesis, we are using a specially devised vessel. I am coming to that. That vessel is called autoclave. Prior to that, we have to consolidate the name. This you know very well. Hydrothermal means temperature as well as aqueous solution. That's the name hydrothermal. At high pressure is also required. So we are using a new device. That device for the synthesis of the nanoparticles by hydrothermal synthesis is called hydrothermal autoclave. So, before entering into the pictorial representation or details of the hydrothermal autoclave, my question is, why this special instrumentation is required? The answer is here. Since hydrothermal synthesis involves high temperature and pressure, that cannot be performed in a common glassware or a test tube, or simple condition is not feasible to perform such a reaction. So, the container must be able to sustain, the reaction vessel must be able to sustain the very high temperature as well as the high pressure. It is possible with the help of a device, with the help of an instrument called hydrothermal autoclave. Hydrothermal autoclave. If you are using some other solvents, you can call it as solvothermal autoclave. Now, the reactants are dissolved in water or other solvent in an autoclave and heated above the boiling point. This is the pictorial representation of an autoclave. It is made up of stainless steel, inside of which is strictly Teflon coated. This is the portion. There is a bursting disc. A stainless steel lid is also there to open that. Inside that there is a Teflon cap, and water or other solvent can be filled here. Salt reagents can be put in this, and it can be heated with the help of a microwave oven or a hot air oven for several hours. High pressure can be generated inside the chamber, and this autoclave can withstand very high temperature as well as very high pressure. So, this instrument is very important as far as the solvothermal or hydrothermal synthesis is concerned. What are the advantages of hydrothermal synthesis? These are some advantages. It is useful for producing various nanogeometries. That is, the obtained nanoparticles may have different geometries. It may be nanowire, nanorod, nanosheet, nanosphere, spherical nanoparticles, etc. So every kind of nanoparticles. So nanoparticles with a different morphology can be prepared by using the hydrothermal synthesis. Next advantage is that it good control over the particle shape and size. We can have a control on shape, we can have a control on size. So we can optimize the conditions, optimize the concentration, optimize the pressure, optimize the temperature, etc. such that we will get uniform sized particles with the desired size. Uniform sized nanoparticles with the desired shape. So size and shape can be controlled in the hydrothermal synthesis. Now we are discussing another important bottom-up approach, that is nothing but co-precipitation. As the name indicates, co, what do you mean by the term co? Whenever we are using co, yes, this term co represents two or more things together. So what is co-precipitation? The precipitation of two or three substances together, more than one substance together, that is called co-precipitation. These are the details of the co-precipitation. In the co-precipitation reaction, the required metal cations, for example, if you wish to prepare iron oxide nanoparticle or iron oxide nanoparticle or iron nanoparticle or something like that, some mixed oxide nanoparticle, you have to take its precursor salt solution as a soluble salt, co-precipitated together. For example, if you wish to prepare Fe3O4, you have to co-precipitate FeO and Fe2O3, ferrous oxide and ferric oxide together. So you are precipitating two substances together from a single solution. A single solution containing two salt precursors subjected to same time precipitation, simultaneous precipitation, you will get the nanoparticles. So from a common medium, and the precipitation is performed as the precipitate obtained may be hydroxide, carbonate, oxalate or citrate. For example, if you wish to prepare Fe2O3, Fe2O3 is ferric oxide, FeO is ferrous oxide. If ferrous oxide and ferric oxide form simultaneous precipitation as their hydroxides, then you will get nanoparticles of Fe3O4. We can enter into more details of the co-precipitation reaction. The precipitate obtained after drying is subjected to heating at room temperature, and at a suitable appropriate atmosphere, these precipitate undergo decomposition to get to the final product. The co-precipitation technique is highly useful for the preparation of the nano powders. We can illustrate the co-precipitation technique by taking the preparation of nano Fe3O4. Fe3O4 nanoparticles can be prepared very well with the co-precipitation method. What we have to do in this procedure? Iron oxide nanoparticles can be prepared by this method by the co-precipitation of Fe2 plus and Fe3 plus. Fe2 plus is precipitated as FeOH twice, and Fe3 plus is precipitated as FeOH thrice. So iron 2 plus get precipitated as ferrous hydroxide, iron 3 plus get precipitated as ferric hydroxide. So you are getting a mixed precipitate of ferrous hydroxide and ferric hydroxide. It evaporates some water and finally you are getting Fe3O4 nanoparticle. In order to cancel 2 plus, you can take a chloride, ferrous chloride and ferric chloride etc. can also be used for the purpose. So this reaction, this is a very popular method. So taking ferrous salt and ferric salt mixed together in 1:2 proportion, add OH minus in the form of NaOH or KOH, then what will happen is iron 2 plus is precipitated as ferrous hydroxide or FeOH twice, Fe3 plus is precipitated as FeOH thrice. The precipitation is simultaneous and these two precipitate jointly eliminate water molecules and you are ultimately getting Fe3O4 nanoparticles. So in co-precipitation, two or more metal ions, same metal ions in different oxidation state is precipitated as their hydroxide or carbonate or oxalate, and that precipitate eliminate water molecule to produce the final nanoparticles. Now, one of the drawback or difficulty associated with the co-precipitation method is that it is too tough, or the controlling over particle size and morphology is very difficult. That is, the particles obtained may be of different size or different shapes. So, it is a difficulty as a controlling of particle size and geometry is, or morphology is a very important drawback. It is not practically possible to control the size and morphology by using the co-precipitation method. Now, we are entering into another bottom-up method. This bottom-up method is called spray pyrolysis. We don't want the much more details of the spray pyrolysis procedure. I mentioned it only because of the significance of this method, since it comes under the category of the bottom-up approach. So, this spray pyrolysis is a method. It is a process which a precursor solution is atomized. It is then evaporated and then decomposed into particles and thin films. Spray pyrolysis include spraying of the metal salt solution on a preheated substrate, drops sprayed onto the substrate, stretches disk and then thermally decomposed. So, we are spraying a precursor salt solution into a chamber, and drops sprayed onto the substrate stretched as a disk, they will spread and thermally decomposed to get to the nanoparticles. Pyro means heating, lysis means fission. We are spraying the salt solution first, subjected to pyrolysis, nanoparticles are obtained on the surface of a substrate. Now, this is the concluding remark on synthesis of nanomaterials. Both the approaches are shown here. So, by the last two modules, including this, we have discussed the two different approaches, their advantages, disadvantages, important methods belongs to each category, etc. This is a consolidation of both the bottom-up and top-down synthesis. From left-hand side to the middle, the synthesis is top-down. From right-hand side to the middle, the synthesis procedure is bottom-up. This represents the complete procedure of the synthesis of nanomaterials. Thus, in this module, we have considered the bottom-up approach in more detail. That's all about this presentation. Have a nice learning experience. Thank you.